Alright, here we go. Picking up or beginning our journey through derivatives. If you have not watched any of the videos on limits, I strongly encourage you to do so because things will get exponentially more difficult if you have a very limited view of what a limit is, no pun intended. But what is a derivative? First and foremost, a derivative is the rate of change. A common physics-based application. It also doubles as the slope of a tangent line, and probably the most important aspect of a derivative, it is the limit of the difference quotient. As we are starting out with derivatives, this could quite possibly be one of the most pivotal topics that you come across. Many people love derivatives because of their rote procedural capabilities. It's very formulaic, it's very algebraic, but there are ways to be asked questions that go beyond just like compute the derivative of x squared, compute the derivative of sine of x squared, etc., etc. And just because you can do that doesn't mean you actually know what this is. So it all begins with a secant line. I'm going to do my best to try and get both of my graphs up here so we can have a side by side. Okay. If you are aware, a secant line, and this might have been the tail end of your geometry knowledge, right? But let's assume we have a point P, which is has coordinates like that, a f of a, and let's go with Q, which has coordinates x, f of x. Let's say we wanted to calculate the slope of the secant line. Right? So if you remember back to your Algebra 1 robot days, slope is the rise divided by the run. So if we were to calculate this, delta f, change in the output, we would have f of x minus f of a. And the corresponding run be delta x, change in the lateral position, which would simply be x minus a. So if I wanted to write this in a different color, so it pops a little more, I'm ultimately going to wind up erasing this, so make sure you get it into your notes. This is going to be a tough squeeze. There we go. Slope delta f divided by delta x, f of x minus f of a over x minus a. Notice it retains similar structures to how you first learned so as an Algebra 1 student. y2 minus y1 divided by x2 minus x1, y2, y1, x2, x1. We've just beefed up how we write our expressions. This here is what we call the difference quotient. Right? Because you might be asking, well then how does this necessarily apply to this idea of derivatives, right? But application 2 of derivatives is the slope of the tangent line. So what is a tangent line? Like I said, I'm going to erase this piece just to have a little bit more room. To conceptualize a tangent line, try to, right, remember this is point Q, try to imagine P and Q coming together, right? So I wish I could, visually push these 2 points together, right? I want the distance between them to become 0 so that they're literally sitting on top of one another. Right, so because the tangent line touches a function, or anything that's tangent to a shape or whatever the case may be, because you did talk about tangent lines in geometry, right? It touches it at exactly 1 point. Right? So let's define this to be P, which is once again still a f of a. Okay? So Q sunk along this function until it's at precisely on P. Right? So Q sinks right onto P. So the secant line rotates, right? So we're kind of shifting downwards slightly into a tangent line. So what's happening here, right, is we calculate the derivative. We are calculating the derivative, right? So f prime of a, that's the notation that we use to define derivatives, is equivalent to the limit as x approaches a, right? So as x approaches a of the difference quotient, right? And once again, I'm running out of space. This is what we define as the derivative, which is nothing more than the slope, right? Because this is the equation, or the structure for slope of the tangent line. So let's write down its definition formally, away from these two images. We're going to consult them often, so I will refer back to them. I obviously won't have a visual, but you should have these in your notes at the very least. Right, so the definition of the derivative says, oops, don't need this no more. The derivative of f of x at x equals a is the limit of the difference quotient prime of a limit as h approaches 0 of f of a plus h minus f of a all over h, which is really equal to the limit as x approaches a of f of x minus f of a, or x minus a. This is the structure that we had used in our visuals. So then you might ask, well, what is this? H represents that initial distance between point P and point Q as part of the secant line. Right? So as that distance from Q to P increasingly gets smaller and smaller and smaller until Q is sitting on top of P, aka their distance becomes 0. Right? We need to make some modifications. So H, in essence, I should write this in a different color. H is really a rewrite of x minus a. Right, so H is that horizontal distance between two points. And the reason why we need this difference quotient is because if something is a tangent line, right, it's essentially, it has one point that touches the function. So we need to calculate the limit in order to calculate its slope. Typically slope, we need 2 points, right? So what's happening with the tangent line is we're taking essentially these 2 points that exist if it were a secant line, and decreasing the distance between them
which allows us to compute the slope of that tangent line. But let's get into one application problem because this section is a bit lengthy, so we're going to divvy it up into two separate parts. So let's say we were tasked with find, actually I don't like the word find, construct the equation of a tangent line to, we'll start easy, f of x equals x squared, and x equals 5. Alright, so if we refer back to our definition, our definition says the limit as x approaches a. The reason why I want to use this one is because we have a defined value that we've been provided, f prime of x, because we need the derivative, that's the slope of the tangent line, f of x minus f of a divided by x minus a. F of x we know is x squared. Let's get into this habit of always rewriting our limit as x approaches. Right, 5 is our defined point that we want the tangent line at. So f of x once again is x squared minus f of a. So 5 times 5 is 25. X minus a, right? Because we don't know, these are just arbitrary values that we are using. Oops, I should not say a. I should say 5. Good catch, making sure you're awake. This we can factor as x plus 5, x minus 5. Then we have a little bit of simplification that occurs. So the limit as x approaches 5, as x plus 5 is 10. Fantastic. But what are we to do with this? Because the question is saying construct the equation of a tangent line. If you forgot, that's perfectly fine. But back in Algebra 1, you learned this structure, which is the point slope form of a linear equation. We have a slope, we have half of a point, right? We know that when x is 5, the output is 25. So we have a point, we have a slope, and thus the equation of a tangent line for y equals x squared at a point at an input of x equals 5 is such. Now you might be sitting at home saying, but it's not in slope-intercept form. But once again, this still yields the same equation. If you want to go put it in slope-intercept form, be my guest. However, if you were my student and you make some type of arithmetical mistake, you end up inhibiting yourself and you will lose a point or two, not the entire thing, but a point or two because of the careless numeracy issues. But I'm going to break this into two parts, so I'll see you very soon in the next one.